Okay, so this was the last slide that we covered, and in this we actually saw that if both C and A in your complex exponent, if both of them are equal to 1, then what happens? So if you see here, we have this C e raised to power of AT. This is your complex exponential. This is your exponential signal. So if both A and C, both of them are complex, then what happens? We can just write C in terms of polar coordinates, A in terms of rectangular coordinates, plug in the value, we end up getting this long statement right here. Then we just take all the values with t on with the complex part on one side and not having complex part on the other side, that so that we have e raised to power of rt into e raised to power of j omega naught plus phi t. Now this part, as we see right here, this is simply complex exponential. The only difference is that instead of one constant value, we have a constant value omega naught plus any other constant value. So makes no difference still. We have e raised to power of j. So last time we were seeing this, that we have this complex exponent. Now complex exponent, again, what that thing is, it is basically a complex frequency also, because it is going to have a real part which is also a sinusoid and imaginary part which is also a sinusoid. So e raised to power of j something t, and that something can be any constant value. And typically we write that constant value in terms of 2 pi times something, because that constant we also refer to it as angular frequency, and 2 pi times something, and that something is actually the frequency. So omega equal to, so this whole quantity right here is basically angular frequency, and typically we write it in terms of 2 pi times any particular quantity, and that quantity is basically your frequency in terms of hertz. So complex exponent has a real part and has an imaginary part. So let's see that this is the real part, cosine, and this is the imaginary part, sine. If it was just complex exponent, then it will be just cosine and sine. And we can draw the sinusoid. Everybody knows what is a sinusoid and how does it look like. Here the difference was that the magnitude, instead of being a constant magnitude, the magnitude was having again an exponent in it. And this actually means that the magnitude also was changing with time, either like this or like this, depending on whether this r that you see right here, if this is positive, then, if r is negative, it is like this. If r is positive, it is going to be like this. Let me just correct this. This is not this, it is basically r less than 0. If r is negative, then it will be a decaying exponent, right? So this magnitude part, if you see with time, the magnitude of your sinusoid is decreasing here, and magnitude with time is increasing here, right? So if we take this first, r greater than 0 or r positive, that means magnitude with time is increasing. So sinusoid that you have, its magnitude is increasing, and this is what we get. The first oscillating sinusoid that you see, this is what you get. If you see the magnitude part, this is what is happening to the magnitude. It is increasing with time. And this is what we covered last time. I'm just repeating it because this is important and interesting. And if your r here was negative, if r was less than 0, then magnitude will be decreasing with time. Magnitude of this complex exponential will be decreasing with time, and you will end up getting something like this right here. So this is again plot of your sinusoid, plot of your sinusoid, plot of the real part of sinusoid. Similarly, we can have a plot of the imaginary part, which will be, instead of that starting from here, it will be starting from 0 right here. It will be going like this. So it will be a sine there. So complex exponent, what that thing is, exponent, what that thing is, that I explained in all the slides that you have seen so far. Now, coming over to the real and imaginary part, they are sinusoids. So if we want to find out about e raised to power of j omega t itself, we know that e raised to power of j something constant times t. This is a complex exponent, and we have called this as complex exponent, complex frequency, or simply frequency, because it has got a real part which is a sinusoid, cosine omega naught t, and it has got an imaginary part which is also a sinusoid, right? So we can plot the real part. If this is periodic and this is periodic, that means both real and imaginary are periodic, that means this is also periodic. And we know that the period can be found out using this omega naught, because omega naught, that constant, we tend to write it in terms of 2 pi f. This f is the frequency, omega naught itself is angular frequency, and if you want to find out time period, that will be equal to, either we can just take it as 1 over frequency, or we can take it as 2 pi over omega naught, one and the same thing. So we can find out the time period for that thing also. So let's call that as T naught. Any confusions here? This complex exponent we covered earlier also. This complex exponent again is something which, especially electrical engineers, they play with this quantity a lot. Computer engineers, not that much, but you need to know what this complex exponent actually is and why it is so important for us. And again, this complex exponent you will see later on in Fourier and other types of transforms, and why we use that. We are going to cover that also later on. Although you have covered that mathematical approach, but once we cover it in this course, it will be practical approach. Okay, now we covered two things, which was energy and average energy or power. So if you want to find out your energy, now what we can do is we can find out energy in one time period. Energy in one time period for this complex exponent. It is a periodic thing. So if you find out energy in one period, that will be from 0 to t naught. Time period is t naught. It will be the signal square times signal square integrated or summed up over the whole duration. Now this square of this complex exponent ends up coming out to be equal to 1. Why is that? Why does complex exponent square comes out to be equal to 1? Any idea? Complex exponent, why that thing turns out to be equal to 1. So if you see this e raised to the power of j omega naught t, we know that this thing is actually equal to, sorry, what is having a lag, cosine omega naught t plus j times sine omega naught t, right? So it is basically this part, right? Just take the square of this. What should you get? It should be cosine square omega naught t minus sine square omega naught t plus 2j cosine omega naught t sine omega naught t. Is that right? What? This is not equal to 1. Is that equal to 1?
Sir, plus sine square minus 2j.
Why? If I take square of this thing, what will be the square? So j sine omega naught t. If you take square of that, sine omega naught t square into j square, what is j square? It will be minus 1. So this is something that we see. Now this confuses people, that what is going on? Why do we say that e raised to the power of j omega naught t square is equal to 1? So to make the life simple, we say the magnitude square equal to 1. And if you remember your complex numbers, we had a plus jb. What was the magnitude of a plus jb? The high flyers in mathematics. What was it? Okay, all of you are high flyers. So this was the magnitude. So if I take the square of that thing, under root goes, it is square of the real part plus square of the imaginary part, right? So same value right here. If I take just square of the magnitude, the imaginary part and real part square, so it will be just cosine square omega naught t plus sine square omega naught t. Clear now? And what is this equal to? Cos square plus sine square, cos square theta plus sine square theta, that is equal to 1. Now this actually brings us to a very interesting fact. You are going to be an engineer now, you are doing graduate bachelor's level studies. In high school, you may have learned something about square of numbers. Remember that a square, what was it? A multiplied by a. Simple, high school, I believe 3rd grade, 4th grade, somewhere. But that is what we teach high school or elementary school or kindergarten guys, that this is a square. So because all they have to deal with is real numbers only. Let's say a is equal to 2. This is the biggest problem for them, and they feel, you can say, satisfied that they are able to take a square of this thing. But all they need to do is that if a is equal to 2, a square is then what? It is just equal to 2 multiplied by 2 is equal to 4. Simple thing, common sense. Now, once you grow older, reach your FSC, you come across complex numbers. Let's say 2 plus 3j. Now if I say a square, that creates confusion like this. We end up getting j and all that. So again, to keep you guys, let's say, comfortable, we say that just somehow the other memorize this. It is the real part square plus the imaginary part square. This is what it is going to be, and just 13. Then don't question, that's it. So that is what we teach, again, FSC and maybe high school. Just give me a second. Now, typically, the actual thing would be the square is actually not this multiplied by this. If it is complex number, it is a multiplied by a conjugate. What's a conjugate? Complex number with the imaginary part sign flipped. This is valid for real number, valid for complex number. Now again, problem comes in once we have a problem like this. If it is 2, 3, 4 and 5. If we have a matrix. Now it can be a matrix or it can be, let's say, a vector. Let me make a vector. Okay. If a is this. Now what is a square? That again is a trouble. So what is a square? Can we find a square? Can we find a square in this thing? Can we find a square? Can we find a square? If you try to find a square by the initial logic, it will be 2 into 1 into 2 into 1. Can they be multiplied? Yes or no? They cannot be multiplied because row and column thing. So they cannot really be multiplied. So what happens in case of matrix? In case of matrix, our squaring thing is basically this. We say that our square is basically a into a. What is this? Transpose. What does transpose mean? Rows and columns gets flipped. So in that case, this will become 2, 1 and 2, 1. Now we can multiply that. We can find out the answer. So for complex number this, for let's say matrices it is this, for real number it is this. What if your matrix has got complex number? If this is a, now what? Yes, then we say that it is basically the squaring part would be a into a transpose and conjugated. What is transpose conjugated? We have a name for this. Anybody ever heard of this? Later on in masters.
Symmetric.
It is not symmetric. It is, anybody else? It is Hermitian. So what is Hermitian? It is taking a transpose and then taking conjugate. Transpose conjugate or take conjugate and then transpose, one and the same thing. That is known as Hermitian. So actual squaring, magnitude squaring is just a into a Hermitian. At times they are just written together as A Hermitian. This is actually squaring. This is actually squaring of the magnitude part, or at times we just say squaring. Now this is valid for any type of number. Now remember, see this. If we have A equal to 2, what will be the Hermitian of 2? Hermitian means conjugate and transpose. What will be conjugate of 2? Still 2. Transpose, because single quantity, not a vector, again 2. So it will still be this. So it is valid for this. If you see this complex number, A is this, and A Hermitian would be conjugated part, which will be 2 minus 3j, and then transpose, it is single quantity, so it remains the same. So this is also going to be true, because this squaring would be just what? 2 plus 3j into 2 minus 3j. It is just A plus B into A minus B. What is this? A square plus B square. What is A plus B into A minus B? A square minus B square. But if you have a J in this B, that minus ends up becoming plus. You end up getting exactly the same answer right here. So same will be true for a matrix, for a vector, for a complex sort of a vector. It will be true for everything. Now this is sort of looking ahead, but later on you will not face any difficulty if you just think of the magnitude squaring part as just the number multiplied by its Hermitian. And this will be true for all. Now we don't teach kindergarten kids this, or elementary or high school kids this, because by that time they are not exposed to matrices, they are not exposed to complex numbers. For them it is good enough that squaring is just number multiplied by itself. That's it. But later on, especially the master's guy, they should know all this. But typically this thing somehow gets skipped during your undergrad, and once people reach masters at that stage, they are getting confused at what's going on. Okay, so that was one way of looking at this part. So if we need to find out this, it will be just real part square plus imaginary part square, or in other words, let me just write it this way, sorry, e raised to power of j omega naught t, that will be the number A, into what will be the conjugate part, e raised to power of minus j omega naught t. Remember, conjugate is just wherever you see j, replace it with minus j. Don't try to just convert it into real and imaginary part and then just flipping the number. So if you just multiply these two together, the powers, they get added. What do you get? E raised to power of this minus this, which is 0, and this ends up becoming 1. So very straightforward, we can directly write this. And that is what you saw once we saw it here. So they assumed you know all this, and directly they wrote 1. But with experience, I know that you guys at times get confused that, okay, why? There are about maybe 5-10 steps that you are habitual of taking, and then it becomes 1. How can we directly write 1? We can directly write 1 if you know what is the squaring magnitude for any number. So that is that number multiplied by its Hermitian. And if it is not a vector or a matrix, it is that number multiplied by its conjugate. So that is one way of looking. The other way of looking at the same problem is, if you are given any complex number, we can represent a complex number as a rectangular coordinate that will be of the type a plus jb. So we can represent this as a plus gb, that is cosine plus j times sine. We know this. The other thing is, we can represent that number in terms of polar coordinates. Polar is basically r e raised to power of j theta. So we can, this is also a complex number. So e raised to power of j omega naught t is a complex number if you want to represent it in polar coordinates. So it is basically the magnitude part, which is again 1, into e raised to power of j, the phase part, which is omega naught t. Right? So what is the magnitude part? Just 1. So if we just see this number as a complex number written in polar coordinate shape, then magnitude of that number is just equal to 1. We can see that magnitude part is already 1. I hope you are getting this. So this is how you see that. Now, as an engineer, if you learn how to simplify things, how to engineer the simplest solution, your life will be very, very easy as an engineer. You will become a good engineer. And if you are that ritualistic sort of engineer who just very good with the, let's say, mathematics part, very good with, I don't know, the theory part. Okay, give me it and I will just fill up 3 pages and give you an answer. Then you may be a good student, you may be having maybe 3.5 or 4 cumulative, but you will not be a good engineer. A good engineer always try to simplify things, always wants to engineer the simplest solution. Okay, so if we just put 1 here and then find out the value, we see that in one time period, the energy comes out to be equal to T naught, which is same as time period. That's an interesting thing. And if in one time period, energy is T naught, if we just consider any one time period, this is starting from any particular point here, let's say this till this point, this is one time period. In one time period, if energy is equal to T naught, if energy was equal to T naught, how many time periods should we have in a signal, in a sinusoid? How many time periods should we have? The whole duration. We have infinite time periods. It's an infinite signal, oscillating signal. So in one cycle, if energy is T naught and we want to find out the total energy, then total energy will be infinity, because it's a cumulative thing. In over infinite duration, the energy will be infinity. This is that second example where total energy is infinity, but we can find the average. Average is basically total divided by the duration. Now, one way of seeing it is that, okay, total energy is infinity, total duration is infinity, it is infinity over infinity, so indeterminate. So we can always just write it here as P is equal to infinity over infinity, so cannot be found, right? That's one way of just looking at it. The other way of looking at it, which is more engineering approach, would be, this is a periodic signal. So whatever we have in one period, that thing is being repeated throughout from minus infinity to infinity. So if we find out average in one time period, that average will be there throughout. Make sense? Because this is a periodic signal, we have so many periods, and these periods go on and on this way and this way. So infinite periods. So we just find out energy in one time period and take average of that energy in one time period. So that will be the average throughout, and that is what is done right here. So one time period is basically T naught, and energy in one time period was also T naught. So it is basically just T naught over T naught, the periodic signal. The average energy or power that we get is actually equal to 1, right? This is just one example shown right here for complex exponent. So a lot of things were covered here for complex exponent, starting from very simple. We can have both C and A real, then just A complex, then both A and C complex, how they look like. Then just we talked about our e raised to power of j omega t, because this is a complex exponent which we will come across again and again and again. And why we keep coming across it again and why it is so useful, it will become clear. If not by the end of this course, by the end of DSP, you will be absolutely clear that why this complex exponent e raised to power of j omega naught t is so important and where all it is used. That was the complex exponent. Now let's come towards more computer engineering part, the simple part. That is for this unit impulse and step signal. So two types of signals we'll see here. What is a unit step signal? What is a unit impulse signal, or step signal or impulse signal? What are these? So let's first talk about unit impulse signal. And then we are going to talk about unit step signal. We covered this earlier also. In introduction, we covered what is a step signal, what is an impulse signal. Did we cover that?
Yes.
Okay, here we are going to go a bit more deeper into this. So unit impulse signal is a signal which is 1 only at, if it is discrete, only at n equal to 0. The value is 1. Rest throughout it is 0. So that's a unit impulse signal, delta n. We have a symbol for this. We call this signal as delta n. That's a unit impulse signal. Now mind you that if you have delta n minus 1, how should it look like? How should it look like? Delta n minus 1. Instead of this being at 0, it will get shifted by 1 time unit towards right. We covered that shifting part. Did we not? Okay, we're going to cover it later on. So let me I'm jumping ahead. So forget about that shifting part. We're going to cover it later on in about 2 or 3 slides later. So let's just talk about unit impulse signal and unit step signal. And unit step signal is a signal which is 0 from minus infinity all the way to n equal to 0. And at n equal to 0, it becomes 1 and then remains 1 all the way to infinity. So this is what your unit step signal is. We have a symbol for that. We call this u of n. So these two signals, delta n and u of n, very, very important. And you will see that your digital electronics, discrete electronics, computer engineering, it will just revolve around these basic types of signals. So delta n, if you just write it mathematically, its value is 0 for all n's except for n equal to 0. At n equal to 0, this is 1. This is how we mathematically write it, that it is equal to 1 at n equal to 0, and if n is not equal to 0, its value is 0. That is your unit impulse. And unit step, it is 0 for all values of n which are less than 0, minus 1, minus 2, all the way to minus infinity. It is 0 throughout. At n equal to 0, it becomes 1 and then remains 1 throughout. So that is your unit step signal. And this u of n, if we just shift it right by 1 time unit, then instead of starting from 0, if we just take this signal and just shift it right by 1 time unit, or we say we delay it by 1 unit, we have u of n minus 1. That signal is basically something which starts from n equal to 1 and then it remains 1 throughout, right? So this is u of n minus 1. What we can do is, if we just take this u of n and subtract u of n minus 1 from it, just see these two, you will end up getting your first signal right here. So delta n we can derive by just subtracting a delayed version of unit step from unit step. We can get it that way also. Any confusions here? Very straightforward, simple types of signal. One is your unit impulse, the other is unit step. So the same thing is true to some extent for continuous time signals also. For continuous time also, we have unit impulse and we have unit step. Let's talk about the second signal first, which is your unit step signal. So unit step signal is 0 throughout. It is 0 throughout from minus infinity all the way to t equal to 0. At t equal to 0, it becomes equal to 1. And then all the way to infinity, it remains equal to 1. That's a unit step signal. So it just steps to value 1 and then remains there. So this is your unit step, and this is how we define it. We write it as u of t. This is u of t. So u of t is a signal which is 0 for all values of t from minus infinity all the way to 0. At t equal to 0, it becomes equal to 1 and then all the way to infinity it remains 1. This is your u of t. So unit step, very similar to what we saw for discrete time, right? No confusions here. The confusion arises here, unit impulse. So it is very similar to this unit impulse that you saw for discrete time, but this is something which requires a bit of explanation. Let me define a pulse. So if a signal starts at any value, t0 or 0 or whatever, and finishes at, let's say it starts from t1 and finishes at t2. So this is your t. So that's a pulse, right? In simple terms, we call this type of signal a pulse signal. So this x of t is a pulse signal. Now, if this pulse is such that area of the pulse is equal to 1, we will call that as unit pulse. So that will happen if, let's say, its magnitude part is 1 and this T2 part is 1. So it starts from 0, ends at 1. If you just find out the area, it will be 1. So this will be what we call this a unit pulse. And this unit pulse, we call it not because of its value, because of its area. So a unit pulse is a pulse whose area is 1. Area under the graph is 1, right? So if we have a unit pulse, then you just take integration x of t dt from minus infinity to infinity. What should you get? You'll get 1 because from minus infinity all the way to 0, this is already 0. We can write it in 3 parts. From minus infinity to 0, x of t dt, plus from 0 to 1, x of t dt, plus from 1 to infinity, x of t dt. That will be your area which we have divided into multiple parts. This is 0. This is 0 because x of t is 0 throughout. X of t is 0 throughout. Here the x of t part is 1. So 1, 0 to 1 dt. And if you just solve it, ends up giving us 1. So in unit pulse, the area of the pulse is equal to 1. Clear? Now, this is a unit pulse. Another example of unit pulse would be that if it starts from 0 and finishes at, let's say, 1 by 4. If you need a unit pulse, what will be its magnitude part? 4. This is also a unit pulse because its area is 1. So this is unit pulse. This is unit pulse. Now, if you further reduce it, let's say we say that 0.1. What will this become? 10. So we can keep going on and keep reducing this. We can keep reducing this. If you keep reducing that, its magnitude part will keep increasing, right? Now, let's take a limiting case. If this duration that we have, let's call this delta t. And this magnitude part that we have, that will be 1 over delta t. Is that right? Now, if delta t becomes 0, if that becomes such a small duration that it becomes 0 duration, what will magnitude become? Magnitude will become not almost, it will be exactly infinity. We cannot represent infinity. That's why we just put an arrowhead right here. And this case where we have a pulse whose duration is 0, we don't call it a pulse, we call it a impulse. The very English meaning of impulse is sudden. So this is an impulse, and in the impulse, the duration of this impulse is 0. The magnitude part of this impulse is infinity. Right? Now you have signal generator in your lab. We can generate this type of pulse. Can we? From signal generator, let's say we put voltage equal to 1 and time equal to 1 second, and oscilloscope we are seeing very nice pulse. We can generate any pulse which has got a finite duration. We can generate this, we can generate this, right? Can you generate this? Why not? 2 reasons. First of all, its time duration is 0 and magnitude is infinity. Now both of these things cannot happen. So this impulse, which we call this as unit impulse, we have a symbol for that. We call this as delta t, and the symbol we just represent it like this, and we put a 1 sign right here. Now this 1 is not its magnitude, it is representing its area. So if you have a unit impulse, this is a unit impulse. The symbol for unit impulse is, as I mentioned, whatever. So this is a unit impulse. And interestingly, if we just compute area under the graph of this unit impulse, what will that be? From here, minus infinity till just before 0, 0. Just after 0, all the way to infinity, again 0. At exactly t equal to 0, the area is actually equal to 1. So this area under this graph is equal to 1. Right? So this is something which confuses people at times, that why we have got a symbol like this for delta t. What does this arrowhead represent? And what does this thing actually mean? Delta t, the value is 0 if t is not equal to 0. At exactly t equal to 0, the value is infinity. So this is something which is kind of different. So this unit impulse, again, as you can see, is a theoretical thing. How do we use this? Why do we use this? If it is theoretical, then why are we actually talking about it? This will become clear once we go into the theory part of it. Now, just like we saw a relationship between your unit impulse and unit step for discrete time signal, there is a relationship between this unit step and unit impulse signal for continuous time also. If we just talk about area under the graph from minus infinity till the time t for delta tau d tau, right? If we have this type of a thing, this is your axis, let's say tau, and here we have your delta tau. So area from all the way to minus infinity till any time t, and you just plot that area from minus infinity. If you plot this area from minus infinity, once the value of t, when the value of t is, let's say, minus 2, minus 3, minus whatever negative value, the area will be 0 throughout. And exactly at tau equal to t, or t equal to, 0, only at t equal to 0, the area value becomes 1. And then as we move forward, the area after this also just remains 1, does not change. So this is what this thing actually means. So this is something which we call as ut. This is your u of t. If you just compute the area from minus infinity till any point t and plot it, that would be your relationship between your unit step and your unit impulse. Or simply put, we say that integration of delta t up till the time t. Or let me just be more technically correct. The area under the graph of unit impulse till the time t is actually your unit step signal. So this is the relationship between both. And the converse is also true. The differentiation, what is the opposite of integration? Differentiation. So if we take the opposite part, that will be also be true. The differentiation of u of t will give you delta t. Why? If you take differentiation at any point, differentiation is rate of change. If you take rate of change at any point, ut is already 0, so there is no rate of change. At all these points, the differential of u of t will be 0. At this point, we have a sudden change. Now differentiation is increase in y over increase in x, to be more specific, rate of change. So in this t equal to 0, increase in y is 1. What is increase in x? 0. So 1 divided by 0 is what? Infinity. And after that, again, the rate of change is throughout 0. Right? Confuses you guys? Okay, if it is not clear right now, once we go further on and start using it, it will become more clear. The major part is that you should know what's a step signal, you should know what's an impulse signal. That's the basic part. Now the only catch in these types of signal is once we talk about unit impulse signal delta t for continuous time. That's a specialized signal, that's a theoretical signal. Okay. This actually, right, I'm just getting started. Okay, let's have 5 minutes break. we have finished the slide set. Rest is just MATLAB. We are not going to cover MATLAB. And once we come back after break, we are going to start with slide set number 3. Okay, just about 5 minutes break, please.